Hey everyone, welcome back, and today let's solve Leetcode problem 1400 titled Construct K Palindrome Strings. So I just want to have a quick note here before we actually get into the problem statement. The code solution for this problem isn't actually too bad. It's pretty straightforward and at least relatively simple, but don't be fooled by that coding solution. This is definitely not too easy of a problem. It does take a while to actually think of that solution, and you have to be pretty well versed or pretty familiar and comfortable with palindromes in the least to be able to really lead to that solution and actually optimally and most efficiently solve this problem in the easiest way possible, which is exactly the solution that we're going to be looking at in this video. So anyways, let's go ahead and dive into the problem statement here. It's pretty short here. Basically, we're given a string s, and we're also given an integer k as our two parameters. And all we have to do is return true if we can use all of the characters in this input string s to form exactly two, or in this case, k palindrome strings, or false otherwise. And really, there doesn't have to be necessarily an order that we choose these palindrome strings to construct or characters to construct the palindromes. They don't necessarily have to be adjacent or contiguous substrings. We just have to use all the characters to form k palindromes in some way or form. So in example 1, we have our input string s to be Annabelle, and in this case we have k to be 2. And so what this problem is really asking us in this test case is, can we form exactly two palindrome substrings using every single character in this input string s? And in this case, our output is actually indeed true. There are multiple different denominations or combinations of substrings or palindromes that we can select from our input string s to meet this criteria. And they also give us some possible constructions. Either we can have Anna and Elbow, which both are palindromes that use all the characters exactly once from our input string s. We can also have an B Na or ELLE or Annelina, right? Plus a B. Something very important to note is, of course, any single substring that has a length of 1, so a character itself, is always going to be a palindrome. And something very important to note here is that in every single one of these palindromes that we could potentially form for possible constructions, it's very vital to understand that they have to be symmetrical to be palindromes, which tells us that we have to have all the characters have an even frequency except for per se 1, and that 1 could just be that little character in the middle. Okay, we can also have two B's here, but either way there would only be at most one character in every single palindromic substring that has an odd frequency, because again, we can't deal with odd frequencies very simply because we have to make our palindromes symmetrical for them to be palindromic substrings. And that's very easy to do with even frequency characters because we can put one on the left end and one on the right end. And we'll see that more as a pattern in the next example as well. In example 2, we have our input string s to be Leetcode, and in this case, k is equal to 3. In this case, we have to output false because there's no way, it's completely impossible to construct exactly 3 palindromic substrings rather, using all the characters of s. And so for that reason, regardless of what denomination or combination we choose to construct palindromic substrings, we will not be able to form exactly 3 using every single character in the input string s. Of course, if we didn't have to use every single character in the input string s, we could have this 1L, 1E, and 1T. L, E, and T separately are obviously all considered to be palindromes, but in that case we wouldn't have used all the characters in our input string s for that example. In example 3, we have our input string s to be true and our k to be 4. In this case, yes, our output is true. And in this case, it's a very straightforward single possible solution. Literally, we just have 4 different characters in our input string s and k to be 4. So we have every single possible substring or construction of every single substring to literally just be one individual or single character. Because again, any character is obviously going to be a palindrome of length 1 because it reads the same both left and right. Okay? And again, in the explanation, as you can see, the only possible solution is to put every single character in its own separate string to have exactly 4 palindroming substrings. So for the constraints here, we see that our input string s is actually quite large along with our k input value as our integer. We see that the length of s is going to be within bounds of 1 and 10 to the 5th power, and k is going to be within 10 to the 5th power and 1 as well. And something pretty nice to know, s is only going to consist of lowercase English letters, really just telling us that we're always going to have valid inputs. We won't have random characters like hashtags or numbers in our input string s, and so we don't have to worry about those weird edge cases. So with the problem statement examples and constraints out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so leading back to the example 1 where I was talking about the odd and even frequencies of all the characters that we can potentially form palindromic substrings with, that's actually a very, very important observation to really make to help lead to the solution of this problem, right? Because as you can see, any one of these palindromic substrings that we can form to potentially use all the characters of S, either they're going to have 0 characters that have an odd frequency for them to be perfectly symmetrical, or they're going to have exactly 1 character to have an odd frequency, and that 1 character that has an odd frequency at most is always going to be in the middle, because we don't have to mirror that element, and so it's okay if it appears an odd number of times, because we only need it once, which is an odd number, in the middle of the substring, right? That is very, very important. Again, to reiterate, basically that observation is that a palindrome is going to have at most 1 character in an odd frequency. And looking at a quick example here that I'm just going to make up really quick, let's say we have the string, I don't know, civic. Civic is indeed a palindrome. It does read the same both forwards and backwards as civic and civic. Civic is indeed equal to civic. This is a palindrome. And something very important to note is that every single one of these characters in this input string as civic, they're always going to have an even occurrence, or they're always going to appear an even number of times, in this case, except for this v. And something very important to note here is that this v is indeed the element that not only has that odd frequency of once, is indeed that element that appears in the middle of this input string. Right? That's very, very important because it tells us that for any valid palindrome, that of course is defined to be a palindrome, there's only going to be 1 odd frequency character that can occupy that middle position. Right? Because for example, if we had an I here, this would still work, but again, I would now be a frequency of odd 3. Right? It would not have an even frequency anymore, it would have an odd frequency because we placed 1 I in the middle. This middle element is always going to have that odd frequency because we don't have anything to mirror with it. It's always going to be a standalone character in the middle, adding 1 to the frequency, which is always going to make its character frequency odd. That's very important to know. Either it can be 1, it can be 3, it can be 5. It's going to be odd if it's in the middle, right? And that's a very, very important kind of observation to really make here. Right, now, how does this actually apply to constructing k palindromes as our k integer input? Because that's exactly what we're actually trying to solve in this case. Well, really, the way we can look at that is basically if there are more odd frequency characters than k, well, then we know we'd immediately have to return false because that would be impossible to construct k palindromes. But you may be thinking, well, why even is that? Why is that the case? Well, let me actually comment this out here, and this one as well, to kind of talk about why that is the case. But first of all, let me reiterate what I just basically said. What I just said was that if there are more characters in our input string S with odd frequencies, that's kind of like our bottleneck in this case, for this problem that we're really kind of checking, then our integer k input in this problem, well then we know it is completely impossible to actually construct exactly I think I'll just call it palindromic substrings. I don't know how they define it here. Yeah, palindrome strings, really the same thing. Palindromic substrings, they're, I guess, interchangeable. They are synonyms. Okay, but why is that? Why do we care about these odd frequency characters so much that if we have more than k of them, we can't form k substrings? Well, the reason why is, let me actually fix the spelling error here. The reason why, very important, is because every single odd frequency character has to be in its own separate individual palindrome. Because we just discussed, any palindromic substring that is actually a valid palindrome, it's going to have at most 1 character of odd frequency. Because if it had more than that, it wouldn't be a palindrome because we wouldn't have enough characters to mirror on both the left and right sides. And so we know, worst case, if every single palindromic substring that we form actually does have a character with an odd frequency, we can't have more than k of them because then we'd have to be forming more than k substrings that are palindromic, which we're not allowed to do, which we cannot even do physically, and so we have to make sure that the characters with the odd frequencies in our input string S always never exceed k. They can be equal to k, but they can never exceed k. Because again, if k is greater, or rather less than, the number of characters with odd frequencies, we don't have enough palindromic substrings to break it into for every single palindromic substring to only have at most one odd character to be mirrored and completely symmetrical, because that's exactly how a palindrome is really defined to be. And something else, very important base case as well, that you may have missed because it's very easy to miss, it's pretty simple. If, of course, k is literally greater than our entire input string s, well, then there's obviously no way, it's completely impossible to form k palindromic substrings, because completely ignore the palindromic part of this problem. If we have to break this substring s, or rather input string s, into more substrings than we have characters, well, it's going to be impossible, because we can't create more palindromes than the number of characters we have in our input. It's literally physically impossible without reusing characters, which we're not allowed to do in this problem. But if neither of those conditions hold true, if neither our k integer exceeds the size of this input string s, nor do we have more characters that have odd frequencies than k, well then great, it is possible, and we can actually group the characters correctly while actually following the above conditions, as we see here, of forming those k palindromic substrings using every single character exactly once from our input string s. So to kind of summarize how our code is actually going to work for this kind of like high-level rundown of the solution, basically we're going to first count the frequency of every single character in S using a hash map dictionary or a counter specifically as a data structure in Python. And then we're simply going to loop over the count and check how many characters actually have an odd frequency, because that's our bottleneck, and then simply just check the conditions to see is k less than the length of string S, and do we have less than k odd characters to form that many palindromic substrings. So let's go ahead and dive straight into the code here. What I'm going to first do is kind of have my first initial base case here. If we don't have enough characters to even form k substrings, let alone them being palindromic, so if the length of s isn't actually exceeding k, well then that means, well, we can't form more palindromes than the number of characters that we have, and we want to immediately return false. A quick base case here to avoid any redundant computations if we don't even have enough characters to meet this problem's criteria. Okay, now it's very simple. Now let's actually grab the frequency of all the different characters to check if they have an odd frequency or not. And we can do this in Python using the counter data structure. So I'm going to call it character count, or char count for short, as you may have seen in my other videos. A pretty good keyword to know. And it's going to be initialized to the counter passing in the parameter of our input string s, right? Again, what the counter really does is it maps every single character to our input string s, to its corresponding frequency, which is frequency is basically the number of times it appears in the data structure, right? So for example, let me comment this out, for example, if s was per se triple A, or I'll keep it simple AA, and then a BBC, in that case, the character count would be equal to a dictionary or a hash map in Python, which we get by these curly brackets. It would be the string A mapping to 2. Why is it mapping to 2? Well, because it has a frequency of 2. The string B also mapping to 2, because of course it does also have a frequency of 2. And then the string S, or rather C, mapping to only 1, because we only see it one time. It only has a frequency of 1 in this input string S, right? That's pretty good to know here, how counters actually work. And basically what we're really going to do here is actually help identify how many odd frequency characters we actually have in our input string s, right? Which we can simply check getting count at this index I for every single I in the counter that has a character frequency that's not even. Okay, now this is going to look a little bit unintuitive for you non-Python users. I'll really explain how this works in a bit. Basically, the odd count is going to be the number of odd characters, or rather characters that have an odd frequency, and it's going to be the sum of every single character, or rather word, in our counter that has a frequency that's not even, right? So the way we can do this using dictionary comprehension in Python is for every single count in the char count values. So I'm going to say char count dot values literally. We're going to sum it by 1 in every single iteration if its corresponding count, so count char, or rather char count, at this index I, right? Basically, if it's not equal to 0. In fact, I don't even have to do that since I'm actually looping through the values. In this case, it's literally just char, or rather count, if it's not actually going to be even. And the way we can check if it's even or odd is basically mod it by 2 and check if we have a remainder. If we have a remainder, that means, well, then it's not actually having an even frequency, and so we can simply just add it one more to the running sum in the odd count variable. Okay, again, this is not very intuitive. This is very, very Pythonic. To reiterate, we're simply calculating the number of characters with odd frequencies on this line here. Odd count is going to be the sum of every single one for every single count in the character count hash map, and dot values really checks for the key value pairs, which in this case are basically just the frequencies of all the characters. So we're looping through all the frequencies of every single character. If the frequency of any character is actually odd, so if it actually has a remainder when modded by 2, well then we want to increment this current sum by 1 of this odd count integer, right? Which is going to keep track of the number of characters with odd frequencies that we're keeping hold of, right? Now, for every odd count that we see, we're simply again adding 1 to the sum or the total odd count integer. And effectively, we simply have to return if that odd count actually exceeds k or not. So if it's actually less than or equal to k. It can be equal to k because then we know that every single palindromic substring that we form is going to have exactly one character that has an odd frequency, and it can also be less than k. Why can it be less than k? Well, then that just means that we're going to have some palindromic substrings that we construct that don't have any odd frequency characters at all. For example, in example 1, if we see here, in this case, the odd frequency is going to be 1. Why? Because the only character that actually has a frequency of 1 is this b right here. In this case, 1 is actually less than or equal to 2, and so this would actually be true. The reason why is because Anna doesn't have any frequencies of odd, or rather any odd frequencies of characters. This only has 1. Okay? That's basically what I was really getting there. We can have less than k characters with odd frequencies. That just means that some substrings that we form that are palindromes won't have any odd frequency characters. In this case, as we saw here, Anna doesn't have any odd frequency characters. We don't need to because we can symmetrically form this to be completely symmetrical, just taking the even frequency kind of property of all the characters and mirroring them with each other across the center here, which is a very good thing to note. And that would make this an even length palindrome, right? So this part always is going to mirror this part. The left part is always going to mirror the right part, right? And again, if this is true, we return true, basically because it's possible to form k palindromes because the number of characters with odd frequency that we're going to have at most one of in every single palindromic substring does not exceed k. And we're simply returning if this condition holds true. If it does, we return true. But if the odd count actually is greater than k, that means we cannot form k substrings because we know that at least one substring that we form won't be a palindrome because it would have more than one character that has an odd frequency, and we simply have to return the Boolean result of that comparison, right? So as you can see, if I were to submit this code, this would actually be accepted. This should be a valid solution. And as you can see, this is really just about as efficient as you can get. So, to kind of reiterate what we're doing as a whole, very simple code here as you can see. Basically, we're just checking, can we actually form k palindromes by comparing k to the length of the string first. If we don't have enough characters, if k is exceeding the length of our input string s, we immediately return false because we don't have enough characters or assets to actually meet this problem's criteria. Then, using this char count character or counter, we're counting the frequency of every single character in the string and storing it in this hash map char count, and then looping through every single frequency, or rather the dot values of this char count dictionary, and adding 1 to the total sum odd count, which if that actual frequency has a remainder with 2, meaning it's odd, and the odd count is going to store the number of characters that have frequencies that are actually odd, and if that result is less than or equal to k, that means the condition is satisfied, right? That means it's possible to construct k palindromes, but if it's not, well then we have to return false indicating, right? So for the memory, or rather for the runtime complexity of the solution, this really is just a one-pass solution, and so the memory complexity is going to be big O of n. The reason why is because, of course, n is going to be the length of our input string s. The reason why is because counting the character frequencies using this counter is going to be a big O of n time, because, of course, we have to loop through every single character to build it. And then for the actual calculating the number of odd frequencies, that's also going to be big O of n. So technically, this is big O of 2 times n, but really simplified because we don't care about coefficients or constants and complexity. This is going to be a simplified big O of n runtime complexity. And for the memory or space complexity, this is actually going to be big O of 1, believe it or not, because we're not actually using any extra crazy data structures here. We're basically assuming that the input is always going to contain lowercase English letters, right? If we don't assume that, well then technically this is actually a big O of n memory complexity or space complexity, where m is the number of unique characters in the string, but we are basically kind of assuming that it's always going to contain lowercase English letters. So technically, you could kind of optimistically say that this is actually a constant time memory complexity, a big O of 1, right? But really, because technically we only have a constant 26 letters in the English alphabet, but really I guess we're using this counter. It is going to somewhat grow with our input because this is an extra auxiliary memory, extra data structure. So really, Otherwise, it's rather going to be big O of n, and it's going to be the number of unique characters in our input string s. So, if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.